This video is for Lesson 11-2, Congruence Criteria. Learning goals are to develop criteria for proving that triangles are congruent and to determine which congruence criteria can be used to show that triangles are congruent. As you have seen, congruent triangles have 6 pairs of congruent corresponding parts. The converse of this statement is also true. That is, if two triangles have 3 pairs of congruent corresponding sides and 3 pairs of congruent corresponding angles, then we would know that the triangles are congruent. Greg's boss asks him to check that 2 triangles in a truss are congruent. Greg wonders, must I measure and compare all 6 parts of both triangles? He decides that a shortcut will allow him to conclude that 2 triangles are congruent without checking all 6 pairs of corresponding parts. So Greg begins by checking to see if just one pair of corresponding parts of 2 triangles are congruent. Would that be enough to know that the triangles are congruent? So let's prove or disprove this statement. If one part of a triangle is congruent to a corresponding part of another triangle, then the triangles must be congruent. If we can prove that this is true, this is a criteria for knowing that triangles are congruent. If we can prove that this is not true, then we would know that it's not sufficient to have only one part of a triangle congruent to one part in another triangle. So let's see if we can find any counterexamples to this statement. If we can find a situation that proves this statement is false, then we can cross this out. It's not sufficient criteria to know about congruent triangles. Okay, one part of a triangle is congruent to a corresponding part of another. Here is one side of a triangle. Here is another triangle, and these are exactly the same length. Let's create a triangle here. Here's the first triangle, and then here's my other triangle. Are these congruent even though these are congruent? And the answer is no. So we have disproved this statement. It is not enough to have just one pair of corresponding parts be congruent. Now Greg wonders if checking 2 pairs of corresponding parts suffices to show that 2 triangles are congruent. Consider this statement. If 2 parts of one triangle are congruent to the corresponding parts in a second triangle, then the triangles must be congruent. Let's prove or disprove this. So again, I'm going to create 2 triangles. I'm looking for a counterexample to this statement. If I can find a counterexample, I know this is false. So let's create 2 segments that are the same length. This is congruent to this. And then let's make another segment that is that long. And over here on this triangle, we'll make a segment that's exactly that same length. And then finish off these triangles. Are these triangles congruent to each other when these 2 parts are congruent to these 2 parts? And the answer is no. These do not look congruent, so that's enough to show that that statement is false. That is not good criteria to know for sure that 2 triangles are congruent. Greg decides that he must have at least 3 pairs of congruent parts in order to conclude that 2 triangles are congruent. In order to work more efficiently, he decides to make a list of all possible combinations of 3 congruent parts. So problem 3. Greg uses a capital A as an abbreviation to represent angles and a capital S to represent sides. For example, if Greg writes SAS, this is going to represent 2 sides and the included angle. Notice how the letter A is in between the S's. So we're saying that the letter A is represented in an angle that's included between the 2 sides. It's the angle formed by the 2 sides. Here are the combinations in Greg's list. SAS, SSA, ASA, AAS, SSS, and AAA. Mark each triangle below to illustrate these combinations. So this one right here, there's a mark on this side, and then a little loop in the angle, and then a double mark on this side. So we're marking up sides and angles of a triangle using little marks and little loops in the angles. These are not the same length as each other. That's why they have a different style of mark. So this has a side and another side, and the angle that's included between the sides. This is what SAS stands for to Greg. Okay, so that takes care of that one. What would SSA be for Greg? That would be a side and then another side, and then an angle. Notice that this angle is not the angle that's included between the two sides that I marked. So this is showing what SSA means to Greg. Okay, the next one we were supposed to show is ASA. So what that means is that there's an angle, and then a side, and then another angle. With the letter S being between the A's, the S is the included side between the angles. And so it's this side here that comes between the two angles that I put marks in. So this situation is what ASA means to Greg. Okay, next, what would AAS be? Well, that would be having an angle marked, and then an angle marked, and then a side. So this is showing AAS. Okay, next, SSS. What would that mean to Greg? It would be to have a side with a mark, a side with a mark, and the third side with a mark. I use different styles of marks because all of these are different lengths from each other. So this is SSS. And finally, AAA. What would that be? That would be a triangle in which there are marks in the three angles. That's supposed to be a double mark there, and then let's use a triple mark there. That is AAA. So there are Greg's abbreviations. Question B, are there any other combinations of three parts of a triangle? And if so, is it necessary for Greg to add these to his list? So if we think about the ways to arrange capital S and capital A's in combinations using three letters, we haven't yet included SAA, and we haven't included ASS. Now, do we have to include these? The answer is no, because SAA is really the same thing as AAS, which we did have, and ASS is the same as SSA, which we had here. And for those of you with tender ears, we don't use ASS in geometry. We don't want to offend anybody, so we're going to write it as SSA. Now Greg wants to find out which pairs of congruent corresponding parts guarantee congruent triangles. So he had these different possibilities up here, but do all of these situations guarantee that triangles are congruent, or are only some of those six possibilities going to guarantee that triangles are congruent? So let's explore this. Three segments congruent to the sides of triangle ABC and three angles congruent to the angles of triangle ABC are given in figures 1-6 as shown below. So what's going on here is we have this triangle, and it has this side from A to C that's a certain length. It has this side from C to B that's a certain length, and so on. It has these different angles with different degree measurements. And so this has split those different parts up so that we're just focusing in on the angle. You see how that angle is the same size as this angle, or that angle B here is the same size as figure 3. Figure 4, this long segment, is the same as that longest segment in the triangle ABC. So what we're asked here is identify which of the figures in part A are congruent to each of the parts of triangle ABC. And I've written them in there. So angle A from the triangle is congruent to figure 1. Segment AB, the longest segment of the triangle, is the same length as this segment, that's figure 4. Angle B in the triangle is the same size angle as figure 3, and so on. For each combination in Greg's list in item 3, choose 3 appropriate triangle parts from item 4. And then we want to create triangles using these parts. We'll use transformations to check whether every triangle is congruent to triangle ABC, and use the table below to organize the results. So the combinations we're exploring are the SSS, SAS, ASA, AAS, AAA, and SSA that we identified in a previous question. In this column it says name the 3 figures used by listing the figure numbers. So to explore the SSS combination, we would want to use the three sides or three segments from up above, which are figure 4, 5, and 6. We're not going to use figures 1, 3, and 2 because those are the angles. We're not going to do any work with angles to investigate SSS. So here we want figures 4, 5, and 6. So what we're asked to do is if we created a triangle using these segments, 4, 5, and 6, those three segments, if we created a triangle by connecting the endpoints of the segments together to form a triangle, would that triangle that's created be congruent to triangle ABC? Is every such triangle that we would create by putting those segments together, end to end, putting the three pieces together, going to be congruent to triangle ABC? And the answer is yes. Now, if we wanted to explore SAS, what figures could we use from that list of 6 figures to explore SAS? The different possibilities are to use figures 4 and 1 and 5, or figures 5 and 2 and 6, or figures 6 and 3 and 4. But the point is that when you create triangles with those segments and angle, would every such triangle that you'd be able to build be congruent to triangle ABC? And the answer is yes. So let's run through the rest of these quickly to determine if these criteria would guarantee congruent triangles. So here are the rest of them and the conclusion. We're not going to take the time to actually take segments and angles of those lengths and try to physically put them together, let's say on our desktops or something, to see what would happen. That would just take too much time for the video. But I want you to notice that these first 4 criteria guarantee that triangles are produced that are congruent to that original triangle ABC. But these last 2 do not. So these last 2 are worth just investigating why they don't work. If 3 angles of one triangle are congruent to the 3 corresponding angles of another triangle, why is that not sufficient to know that they're congruent? Well, here's a quick example. Let's say that we had this triangle, maybe there's even a 90-degree angle here, and that we create this triangle with a 90-degree angle here. Let's say that this angle and this angle are congruent to each other, and that this one and this one are congruent to each other. Are the triangles congruent even though those 3 angles match up perfectly with those 3 angles? And the answer is no. And that's why knowing that 3 angles of one triangle are congruent to 3 angles of another triangle does not guarantee the triangles are congruent. Now this last one, SSA, this one didn't work either. Here's a quick picture showing a counterexample. Let's say that this is the bottom of one triangle, and that here's the bottom of the other triangle, that these are exactly the same length. And then let's say that this is another side of this triangle, and then over here I'm going to draw a segment that same length right there. But notice how I changed the angle here and here. Okay, so here are 2 sides the same, and then let's make this third angle right there. Let's make that angle exactly the same as this angle. So here we have these 2 sides the same, and then the non-included angle. So side, side, angle, but these triangles are not the same size and shape. So just because you have side, side, angle with little marks on them does not guarantee the triangles are congruent. So these first 4 criteria that Greg was testing turned out to guarantee congruent triangles, but those last 2 criteria did not guarantee congruent triangles. So next question, what is the list of the different combinations that seem to guarantee a triangle will be congruent to triangle ABC? These combinations are called the triangle congruence criteria. That list would include side, 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 angle, side, angle, side, angle, and angle, angle, side. These are our 4 triangle congruence criteria. Do you think there is an angle, angle, angle triangle congruence criteria? And the answer is no. and we had already drawn a counterexample for that. Greg realizes that it's not necessary to check all 6 pairs of corresponding parts to determine if 2 triangles are congruent, because the triangle congruence criteria can be used as shortcuts to show that the 2 triangles are congruent. Example A. Let's take a look at what the questions might look like that go with this geometry concept. For each pair of triangles, write the triangle congruence criterion, if any, that could be used to show that the triangles are congruent. Can we know for sure that these are congruent when we know that that side and that side are congruent, that this side and this side are congruent, and that that one and that one are congruent? Yes, we can. We can use the SSS criterion. Question B. How about this? Can we prove or know for sure that that triangle is congruent to that triangle? Well, initially it doesn't look like we have enough information. If we know that this angle is congruent to this angle, and we know that because they have that same style of loop in the angle, and we know that this side is congruent to this side, is that enough to know the triangles are congruent? Well, that by itself is not enough. But I want you to notice this angle and this angle are formed by the intersecting lines. These are vertical angles. And we had a theorem from earlier in the year that said vertical angles are congruent to each other. So even though those didn't have little marks in them to begin with, we can put marks in them ourselves because we know about vertical angles. Now look what's marked. There is an angle, another angle, and the side that's included between the angles. We can use angle, side, angle to know for sure that that triangle is congruent to this triangle. Here are some try these questions, so I'm going to pause the video for you to attempt these. And here are some check your understanding questions, so let me pause the video again. So in this lesson, we looked at some criteria involving sides and angles in order to prove that triangles are congruent to each other. We came up first with a list of possible criteria, and then we determined which of those criteria actually worked. That was the second learning goal here. Recall that there were 4 of them that ended up working, and abbreviations for them are SSS, SAS, ASA, and AAS.